Excellent. Okay, everyone's where they need to be. We'll start with Aaron.
Okay, great. Yeah, thanks for that intro, Melissa. I'm going to be talking about image access with the butler. So thank you for tuning into this very important topic because the butler is the so-called middleware that connects algorithmic work like pipeline tasks to the underlying data, but in a way that abstracts away the need to know things like file formats or file names under the hood. So it's a very important topic, but it's also a relatively technical topic. So thank you for being bold enough to try this out with us. This is just an overview. We're almost at the end of the Rubin Data Academy now, but for 2025, the Academy is focused on beginner level use of the Rubin Science platform and the newly released Data Preview 1 data products. And we're running 10 different sessions, morning and evening for a global audience, and also repeating them in a certain pattern to try to make sure that folks everywhere or most everywhere have a chance to tune in where they want to. Just starting with some common announcements across the different presentations that we have. One is that we have this resource called the Rubin Community Forum, community.lsst.org. This is a place where Rubin staff are there to help you. And so this is a place for any questions about or issues with the Rubin data products, services, or tools, and to raise a new issue, say, or start a new discussion, you would make a new topic there. And in particular, Rubin staff monitor and respond to all new topics in the support category. So that's where to go if you have an issue where you're needing a response to get unblocked on something, for example. Another good important reminder in the context of what's been going on this week is that DP1 was released at the start of this week. And so there's this very nice data release documentation website for DP1, dp1.lsst.io. It has all kinds of great just overview of the processing, the data products, the observations, and so forth. It's a great place to learn more to get started. It also has information about citing Rubin's DP1, so there is, or perhaps we should say will be, a paper on Rubin's Data Preview 1, and the current draft is already publicly visible online at this rtn-095.lsst.io webpage. Also, if you go to the documentation under data products and you go to the page for a specific type of data product, that will give you the relevant DOI to use when citing that type of a data set used from DP1. Then more generally, for information about Rubin Observatory geared towards scientists, there's the For Scientists section of rubinobservatory.org, which is great to check out if you are interested. So in this session, again, we'll focus on image access with the butler. Mostly we'll be doing probably a couple of hands-on tutorials. We'll probably get through the first 2 or so of these. And there will be, at the start, before we go into tutorials, a little bit of overview of key concepts in butler terminology to help set the stage for what we'll see hands-on in the tutorials. So yeah, the butler is a powerful and important piece of the LSSD science pipelines. And it comes with its own terminology in terms of how you refer to astronomical data and how it's organized. So it's really important to start off by just making sure we're on the same page about this terminology. I'd also note that there's this pipelines.lsst.io website, which has full documentation for all of the LSSD pipelines. And in particular, there's this /middleware URL, which will lead you to a bunch of good resources to learn about the butler, so like an FAQ and other information there. Again, middleware is kind of another term, or well, I guess we should say that the butler is the middleware for the LSSD science pipelines that connects up the algorithmic work to the underlying data, but in a way that abstracts away the need to know specific file formats or file locations on some file system or in some bucket on the cloud. And then this slide has kind of like a bullet pointed list of the terms that I think are relevant to go over before we jump into the tutorials, but there's also in dp1.lsst.io at the URL listed there, a kind of prose version of the same overview that turns the bullet points into a few paragraphs that you could read if you're interested. So the sort of highest level first concept we need to know in terms of the butler is what's called a repo. And just as an example, a concrete example, you can think of a repo as being like a top-level directory within which various data, files, and directories and subdirectories and so forth are organized on a file system. So maybe you would call your top-level directory DP1 if the repo was representing the data products within DP1. But really, this is just a specific example to try to give you a flavor of what's going on. The butler repo concept is more general than the specific example. For example, you could have a repo that lives in the cloud in a bucket where you don't really have a conventional file system, but this is just a nice way to sort of conveniently get started thinking about it. A data set is a singular entity, which sounds a little bit abstract at first, but we can make it a little bit more concrete. We can say a couple of examples here as far as what would constitute a data set. So a data set is an image or table section, for example, as it is stored. And so an example of this would be a visit image for a single visit detector pair. So the visit, i.e. the exposure, plus the detector identifier number uniquely defines a CCD image within the broader DP1 repo. Or another version of this, another example of a data set would be an object table for a single tracked patch pair where tracked and patched together define a specific footprint that, say, a coad would be made on within DP1. Data set types are like a category of data sets. You can imagine examples here being a visit image. So again, a single detector from an individual exposure. Another data set type is object, where object could correspond to a specific object table. And in addition to the category, there's also a corresponding storage class, which you can think of as being like how this object is represented in memory in Python as a Python class. And there's also a set of dimensions that helps you specify a specific data set within a given data set type. We'll get to dimensions a few bullet points from here. So as I mentioned, the storage class is how the data is represented in memory. In images, you'll commonly see within DP1 and the LSSD pipelines in general that there's an object called exposure, a class called exposure F, which holds the images. So you can kind of think of this as being like a representation of the data that includes not only the pixels of the image, but also ways of including metadata that's useful, like the WCS. And then for tables, the storage class is something called ArrowAstroPy, which is a way of representing two-dimensional tables in Python. So dimensions you can think of as the keys that identify data sets of a given type. So examples of dimensions would be a visit, a detector. So, a detector could take on the values of 0, 1, 2, 3, all the way up through 8 in DP1. Tracked, patch, and band are other examples of dimensions. And then dimension records are kind of like instances of dimensions. So each dimension has a corresponding list of values that it takes on, say within the repo. And a dimension record represents an entry in this list providing information about a specific instance of a dimension. So an example of a dimension record would be if the dimension we're considering is band, then one of the dimension records would be G-band. There's a little bit more, as we'll see in one of the tutorials we go through, there's a little bit more than just G-band there. There's actually other metadata that can be attached to that dimension record. For example, the physical filter that's being used. So another concept we'll come up with in these tutorials is what's referred to as data ID, and this is the combination of keys and values that uniquely identify a data set. We'll see some concrete examples there, so I won't go into it too much now. And then collections you can think of as being like different versions of the same data set, potentially within the same repo. And this could happen if you had, say, different processing runs within the same repo, like V0, V1, V2, whatever you might want to call them. But for DP1, we've kept things simple for users, and there is effectively only one collection, and we'll see what the name of that collection is and how to use it in the tutorials that we're about to go through. So again, we're going to go through several tutorials. I suspect we'll probably only get through the first two, but that's okay because these are all available conveniently on the RSP for you to run at your own convenience. And before I jump into the tutorial notebooks, I just wanted to stop and see if there's any questions before we get into the tutorials. It looks like no questions, so let me get started with the tutorials. So the first step you want to do in terms of following along with these tutorial demos is that you would go to data.lsst.cloud, which is the homepage for the Rubin Science Platform, the RSP. And you would click on the central panel in the middle here that says notebooks, to get to the notebook aspect, I'm already logged in there, so I won't go through this myself. But when you click notebooks, the first thing that'll happen if you aren't logged in is that you'll be prompted to authenticate using whatever authentication mechanism that you chose when you signed up for the RSP with an account. And then the other thing after you authenticate, if you're starting a new session, is that you'll be prompted to make certain choices about the container that you're using for your notebook aspect session. And so for the purposes of these demos, what we want to choose is the default version of the LSSD pipelines when you get to that container choice screen, and that is R29.1.1 is the pipelines version we want. And we also want for all of these tutorials to choose the large option on the server size, which just means that you get more CPUs to work with and more memory to work with. So once you've logged in, you'll arrive at a landing page. I closed out the landing page, but you'll arrive at a landing page that looks like this. I'll close it out for now since we're not focusing on that for this session. And then to get to the tutorials themselves, you would go to the tutorials tab at the top and then go down to DP1, and then you go to the 100 series, how to use RSP tools. And then from there, you would go to 104 series. And to start off with, we're going to do 104_1, but we'll very likely get to 104.2 as well, and then perhaps 104.3 in addition to those. So I've already opened 104.1, and let's get started with that. And the title is Getting Started with the Butler. So learning objective is how to use the butler to access image data. That's the theme of the session. The LSSD data products we'll focus on here are deep coad, which are, as it sounds like, the deep co-added images that one would typically expect to be using if you were doing something along the lines of trying to do extragalactic science, trying to find the most distant, deepest, faintest galaxies possible. And then visit image, again, that's like one detector of one exposure. So you can think of that as one CCD image. So these are the two types of images that we'll be focused on here. So right, the butler is the LSSD Science Pipelines interface for managing, reading, and writing data sets. And we refer to it sometimes as the middleware. So why should we use the butler and when should we use the butler? The butler enables users to both search for and retrieve data based on its properties, for example, sky location, band, and date of the observation, without having to know all the under the hood details about how files are stored, whether they be FITS format or some other format, whether they're on some file system or not, in more something like the cloud. It abstracts all this away, and all you have to do is just know how to identify the data set of interest, which we'll get to in a moment. So there's different ways of getting access to images through the RSP and all the tools it offers. So it's recommended to use the butler when you're accessing image data in the notebook aspect, and it's definitely necessary to use the butler when you're going to be doing something like running the LSSD science pipelines tasks on the images that you load in. For example, if you wanted to rerun the source detection or the measurement of properties of sources in the deep coads or creating custom coads. Then there's other use cases where actually other forms of image access are more appropriate. So if you're just interested in like pulling up a full image and perusing it by eye, then you can do that just fine with tap or with the simple image access tool. And then also if you want to do cutouts, there are ways to do that with something called SOTA. So if you just wanted to make a series of little cutouts and look at them by eye or arrange them into a nice montage for a figure or something like that, you wouldn't necessarily need the butler. Really, when it comes in is if you want to be uh, running tasks or analyses from the LSSD science pipelines on these images after you load them in. So this tutorial, again, it's getting started. It's relatively limited in its scope. We only demonstrate how to create an instance of the butler and how to use it in a simple and basic way to search for and retrieve images. So as is customary for all community science team tutorial notebooks, we start out with sort of the pre-matter things like imports and setting up other aspects of the environment or the display. So the first thing we do is we're going to import a few modules. We're going to be importing the butler class from lssc.daf.butler, where DAF is data analysis framework, I believe. And then also this timespan object from the butler, which is going to help us to select exposures based on exposure time. We're also going to pull in AFW display from lsst.afw.display to help us display images. And we're going to pull in astropy.time to help us define time coordinates so that we can use that with the time spans from the butler. So let's import. And then the next step is to set up the Firefly viewer, which should open a new tab. We were noticing in just the few minutes before the session started when we were running some testing within the CST team members that some of us were seeing some inconsistency in whether this was actually popping up a window. It should pop up a window if it's working correctly. So if you run the cell and it executes successfully and you don't pop up a window, then that's a little bit unfortunate for the sake of following along with the demo. But at present, we think that probably isn't your fault and is something on the back end that we'll just have to live with for the time being. So here we go. In my case, it opened this. Yes, thank you, Melissa, for keeping an eye on whether that is working for folks or not. So in this case, I had a Firefly window open just in case there would be any problem there. And so I do have a Firefly tab and it has an image loaded into it already. But if you opened it from scratch, you wouldn't see an image. Okay, so the first thing we do, and this is common across many of our tutorial notebooks, is to create an instance of the butler. And to do that, you just call this capital butler constructor, but there's two key arguments you need. The first argument is the repo name, and in the case of data preview 1 on the RSP, the repo name is simply dp1 all lowercase. And then the other thing that you need to specify is what collections to look for within that repo. Again, we're keeping this simple for users within data preview 1. We only have one collection and that has everything you need in it. So the collection name is just this LSSD compcam just dp1, and that's a common. This invocation of butler with these exact arguments is something you'll see repeated in various tutorial notebooks because that's just how you begin working with the butler and the repo for dp1 on the RSP. So now we're going to show some various ways of querying and retrieving images. The most common butler image queries constrain things like the band, which is the filter, the sky location, and or the time of observation. So to retrieve an image using the butler, you first want to choose what type of image. In this case, the examples we'll use would be either a visit image, a single exposure, single detector image, or a deep coad image. Next, you want to define the query constraints, for example, based on sky location or band or the time of the observation. Then you actually issue the query to the butler to find out what within the repo and the collection actually meets those constraints of that data set type. And then lastly, you want to retrieve some actual data from among the potential data sets that meet your constraints. So let's get started with an example for deep coad images. And here we're going to use an example from the Extended Chandra Deep Field South, ECDFS for short. This is a very nice field of observations that has relatively deep coverage among the fields in DP1. There's a nice page on dp1.lsst.io under observations that gives you a full table of the RA and DEC at the center of each field. So that's where these RA and DEC values came from. And then we'll just choose our band somewhat arbitrarily for the sake of illustration, for the sake of having a concrete example to work with. So the butler, in terms of identifying what data sets of a given data set type meet the constraints that are of interest to you, has this ability to do a query, and the query syntax is SQL-like. And so the first example we're going to do here is just showing how you can explicitly construct a query string in this SQL-like syntax that expresses your desire to have R-band and also to have a patch, which is the footprints that the deep coads are made on, that overlaps with a given RA deck point, the one we defined before. And so the way that's done is in this cell where it uses the formatting of a string to embed the R band and also to embed the RA and deck coordinates. I'll also mention that in terms of this syntax here for the SQL-like query, there's a really nice page within the LSSD pipelines documentation that explains all the different operators you can have, like overlaps and in and so forth. And I found this page super helpful. So if you're looking to dig in more and know exactly what the range of different operators you can have in a string like this is, or what the syntaxes are for different things, I highly recommend looking at that page. So now that we've defined the query strings, we're going to use a method called query datasets that is called on our DP1 butler object. The first argument here is just the dataset type that is of interest to you. And again, we're starting off with deep coad. We'll see another visit image example later. And there's a where keyword argument where we're passing the query string that we fully constructed before. And what is returned is not all of the data itself, but it's like references, or you can think of like pointers to the data sets that actually meet this constraint. So now that we have a list of pointers to the data sets within DP1 that meet the constraint we're interested in our type deep coad, let's go ahead and actually read in one of those deep coads. And the way that you do that is that you call butler.get method with the first data set pointer in that list of data set pointers that we had. This will take a couple seconds because, again, this is really reading in like the pixel data and the metadata and so forth. Then here's where we display with Firefly. Again, if there are any lingering Firefly issues, this may potentially not be possible to follow along with right now. But here's what it pulls up. So the nice thing about this, as opposed to just using matplotlib in cells in the notebook, is that this is a very flexible and interactive image viewer. You can zoom in, you can pan, do all types of different operations in here. And so this is just a really nice way to look at the image in a flexible way that's not constrained by being directly within the notebook. And then as a matter of good practice, we generally try to delete any variables that we're not using anymore or going to overwrite or could free up some memory. So let's do that. Okay, the next data set type we're going to look at is visit image, and we're going to do a few things different in this case. The first thing we're going to do differently is that we're going to use a time-based constraint. And the second thing that we're going to do differently is that we're going to do a little bit of a different way of constructing the query argument that's passed to Butler query datasets using this bind argument, and I'll show that in a moment. So the first thing we're going to do is define two timestamps using astropy.time objects that span about 1 day total. Note when we do this that the LSST pipelines use the TAI time system. This is a technical detail I won't go into fully, but just keep that in mind. And that's why there's the scale equals TAI in both of these calls that create time objects from AstroPy. And then we create a Butler timespan object by feeding in those two AstroPy time objects. And we can run that cell. Okay, so now we're going to, again, find a list of dataset pointers that meet specific criteria associated with this time span. And we're going to focus on the visit image dataset type. So that's the first argument now. It's visit image. It's no longer deep coad as it was before. And then here you can see that the query string has been input and constructed in a somewhat different way. So there's the syntax that you can see where, for example, band.name equals :band. So the colon band or colon timespan or colon array_dec that you see in here are ways of expressing what variable you're going to use as the key name in the bind parameter dictionary. So basically when you pass in the dictionary to the bind parameter, it looks at, well, there's :band, so I better check the band key in the bind parameter that's been sent in. And so it essentially like fills in your query string for you such that you don't actually have to fully construct the query string yourself. Then you can also see that there's an order by at the end. And this shows that you can do order by not just by a dimension, but also attributes of a dimension, right? So it's doing visit.timespan.begin. So what it's saying is order by the beginning of the time span of the visits, of each visit. So let's run this and we'll get a list of data set pointers. And then as we did before, we can just read in the first of those and get the actual image itself. And then we will attempt to display this with Firefly. As we did before, it should put the new single exposure, single detector image into the same Firefly window. And indeed, that looks like the case, right? It looks like this image is a bit noisier, which makes sense. Didn't mean to click on that. So indeed, we've loaded now a single exposure, single detector image, and put that into Firefly so that we can view it, pan and zoom, and so forth. Now let's, again, as a matter of good practice, delete any variables we don't need anymore or anything that may be taking up memory. Now we're just going to illustrate another way of retrieving and querying data with the butler, and this is retrieving images by data ID. So the data ID is a dictionary, the components of which uniquely identify a data product of a given data set type. And so, yeah, if you happen to some way or another know all the components of a data ID of, say, the deep coad you want or the visit image that you want, then you could go ahead and just directly retrieve those data products from the butler without needing to do one of these queries to find out what meets your constraints, say. So let's do an example first of deep coad again. So the deep coads are uniquely identified by their band, by their filter, the tract and patch, which define the spatial footprint that you're working with for the coad image, and the sky map. And the sky map is kind of like a meta parameter that defines how the sky has been tessellated, and that in turn tells you the mapping from tract and patch to actually where you are on the sky. So again, the necessary data ID components for deep coad are the band, like UGRIZY for DP1, the tract, which is a subsection of the all sky tessellation of the LSST sky map, about 2.8 square degrees. And then within a tract, there are a 10 by 10 grid of a total of 100 patches. And so a patch is a subsection of a tract about the size of an LSST cam detector, 1/100th the area of a tract. And the sky map is the all sky tessellation of the LSST tracts and patches. One thing to note is that patches and tracts overlap at their edges. So two deep coad images in this notebook are returned as containing the search coordinates because those coordinates are near the edge of two adjacent patches. That won't always happen, but it can happen sometimes. Thank you, Douglas, for sharing the slides. That's a good thing to remember. Okay, so let's re-execute one of the queries that we already did before for deep coads. In this case, we're using this bind syntax again to fill in the query string with the band and the RA and dec of interest. And then in this case, we're going to loop over the pointers to the data sets. In each case, we're going to print out the data ID just so we can see this in action and see, okay, yeah, the data IDs of the retrieved deep coad data sets, indeed, they have a band, a sky map, a tract, and a patch, which are what allows you to uniquely identify each of these two deep coads. So the next cell just has an example of how you would use a data ID, one way that you would use a data ID to actually read in the deep coad. So in this case, we're again using butler.get. Deep coad is the data set type, which is the first argument. And the way we're doing it here is that we're actually splitting the data ID such that each key of the data ID becomes a keyword argument to butler.get, right? So there's a band equals R, tract equals 5063, and so forth. And so this is one way that you can call butler.get with the data ID is splitting out into multiple keyword arguments. There's another way of doing this. It's probably just a matter of personal preference, but you could also define the data ID as a dictionary. And in that case, the keys would be the dimensions that you have, and the values would be the specific values that you want for your return deep coad. And so this is a way of compressing it into now there's only one keyword argument to butler.get, right? So instead of separately specifying a bunch of keyword arguments, you just have the one data ID keyword argument, which is a dictionary that holds all of the keys and values of the data ID. So now we're going to read in this deep coad. Then let's skip the displaying here since we've already seen this deep coad. And then we'll delete it for the sake of freeing up memory. And we can do similar things now with visit images as opposed to deep coad. We're just going to illustrate how you can retrieve a visit image, so a single detector from a single exposure, using the data ID that you already know somehow or another. So a visit image is uniquely identified by the visit identifier, visit, and the detector number. The band doesn't need to be specified for the data ID of visit image, and this is because the band is a property of the visit. So in other words, a visit, also referred to as an observation or exposure, uses one filter. So there's some level of redundancy in these dimensions, and you don't need to always specify every possible dimension in order to get a unique data set. We'll see some more examples of this in the next notebook, in terms of how you can figure out what actually are the required dimensions to fully specify a data set of interest. So let's just go with this one visit identifier, 2024-11, so on and so forth, and detector 5. This is actually one of the data set references that was returned earlier on when we were querying for visit images. So again, we'll use the butler.get method, visit image. The first argument is the data set type. And then we'll split it out in this first case into one keyword argument per key in the data ID dictionary, right? So there's a visit equals and a detectors equals. And if we run that, this will read in the visit image. And then you can see, I won't go through it, but there's this optional cell here where you could do something analogous to what we did for the deep coad, where you turn the data ID into one single dictionary and pass that as one keyword argument, the data ID keyword argument to butler.get. One other nice thing about the objects that are returned to you from butler.get, so from using the butler, is that you not only have the pixel data, but you also have other metadata. And so here are some examples of looking into the metadata from the object that you retrieved from the butler, in this case, a visit image object. So if we print visit image.filter, so that's the .filter attribute of the visit image object, you get returned rband. And if you print the date, the way that you get to that is first through the .visit info attribute of the .visit image, and then the .date attribute of visit info. So let's do that, and we can see, okay, this was apparently on November 9th of 2024, which makes sense given the time frame of the DP1 observations. And then let's just clear up the memory again by deleting that variable. One other useful thing you can do with the butler is that sometimes you may only want the metadata, or it may be efficient to get the metadata without having to read in all the pixels of an image of interest. And that is indeed possible with the butler. So again, the way you do that is you use this butler.get method. And the first thing that you pass in is now not just the data set type, but it's the data set type with the attribute that you're specifically interested in getting that piece of metadata for. So it's visit image dot attribute, which in this case is dot filter that we're interested in. You can see here we're passing the keyword arguments that define the data ID again. So let's see what that returned. Indeed, it returns rband as we've been working with this whole time. So clear things up at the end. And then next step was going to be to move on to the next tutorial, but if there are any questions, we can pause for a moment here before going on to the next tutorial. Okay, I'm not seeing in the chat any questions or hearing any. I have a weird Zoom window here that's kind of in my way, but that's okay. So yeah, the next tutorial to go through is 104.2. Again, you can get to that if you haven't already by using the tutorials drop-down menu near the top of the screen. And then selecting this one from the 100 series. So the learning objective here is basically exploring more about the Butler collections, data sets, dimensions, and schema, rather than just looking at a couple of images. So this is more digging really into trying to see if we can wrap our head around some of these key concepts that we talked about in the slides before we got into the tutorials. So this tutorial demonstrates how to explore the Butler, how to discover what kind of data is accessible, and the schema associated with those data. Also, which dimensions to use to query and retrieve data sets, and how to visualize the metadata. So we begin in a very similar way to what we had done before. We always start off by importing necessary packages near the very beginning of the notebook. Um, Again, we're going to import this butler class from lsst.daf.butler. We're going to import a couple of spherical geometry packages from the LSST software stack. We're also going to import some plotting utils from the LSST software stack, and then some relatively common things you encounter within Python like NumPy and matplotlib imports. Again, we're going to start off with the same invocation to create ourselves a DP1 butler instance. So you just call the butler constructor. Again, the repo name is lowercase dp1, and the collection is lssdcomcam/dp1 as it was before, and as it will be whenever you're working with DP1 data products currently on the RSP. We're also going to define some plotting style stuff. I won't go into the full details for the sake of time. We're also going to define some more plotting stuff specific to LSST and its bands and how those map to the colors in the color map of the plotting. So this is the type of stuff that we always try to get out of the way at the very start of the tutorial so that it can be useful for the rest of the tutorial without interfering with the sort of train of thought that's going on. So let's start with repositories and collections. These are two of the concepts that we talked about in the slideshow at the very beginning. So repositories are defined by data release, for example, DP 0.2 or DP1. DP1 is the one that's currently of interest because it just come out and it's real on Sky data. Yeah, so in the section above, the DP1 repository and this collection that it has were defined when the butler was instantiated. Any queries for data run with the butler would look only at that collection within that repo. You can print a little bit more information about this collection by doing butler.collections.query.info, and this will print out some info. I'm not sure at the moment, not sure too much of it needs to be discussed. Maybe some of it will become a little bit more apparent after a few more cells, how it relates to other things that we'll see. The other thing you can do is list all available repositories to you on the RSP. And that is, so there's DP02, which is data preview 0.2, which was simulated data, which we had been working with previously before DP1 just came out. And then there's DP1, there's DP02 remote, which is kind of a technical thing that I won't go into. But anyway, there are multiple repos there for the butler on the RSP. It's just that for these tutorials with DP1, we're focusing on the DP1 repo, which has everything you need for DP1. So then collections are groups of self-consistent data sets, and you can think of this as meaning like the outputs of a processing run that uses a single set of calibrations. So one thing you can do is that you can use your butler object to query for all the collections that are available. Again, for DP1, you only use the one that we mentioned before, this lssdcompam/dp1, but nevertheless, for the sake of illustration, we can look a little bit deeper and say, what are the collections? So the syntax here is butler.collections.query. Star just means you want to query regardless of the name of the collection just to see everything that's there. For the sake of illustration, we can probably run this now. And indeed, behind the scenes, there's a whole lot of collections. And so one thing you may have noticed with the previous printout that gave a little bit more details about the LSSD ComCam/DP1 collection that we use as end users is that it's a chain collection. And so what a chain collection really does is it actually sort of has a list of collections that one searches in order, the butler searches in order behind the scenes in order to identify any given data set. So probably some of these collections are being used behind the scenes with the LSSD ComCam/DP1 collection, but fortunately we can just instantiate a butler with only that one collection, even though under the hood there may be more collections than we had initially thought or realized. Okay, so now let's get into data set types. Again, this was one of the key concepts we talked about earlier in the slideshow. Commonly used image data set types, and we just saw these same two in the previous tutorial, are deep coad and visit image, with visit image being like a processed single detector image from a single visit. And then commonly used catalog data set types are object. So object means the object table, which is measured from the deep coads, and then source means source table, which is measured from visit images. I'm not sure we need to go into uncommenting these, but suffice it to say that you can use the butler to query for the full list of dataset types that are available in the DP1 repo, and it's quite a long list. You can uncomment and check it out if you want, but the upshot is really that there's a kind of core list of data products like visit, image, deep coad, object source that you're really going to be working with the vast majority of the time. And those are the ones that are focused on in the tutorials and also in the dp1.lssc.io documentation. So next we get to the topic of dimensions and elements. So we talked about dimensions earlier. Now we're introducing elements, which is a closely related topic. But the dimensions and elements are the properties of a data set type that can be constrained in a butler query. So you can kind of think of the elements as being a slightly broader set of concepts that can be used to make a constraint in a butler query, even if they're not properly dimensions. So commonly used dimensions are, as we've seen, band, tracked, patch, which identify, say, a coad footprint, visit, and detector. And then a commonly used element, which you may see in this tutorial and other tutorials, is called visit detector region. And so this is kind of like a representation of the footprint on the sky that a detector in a given exposure traces out. And so you can kind of see how this is a more general, broader version of a dimension, because it doesn't really seem practical or sensible to try to, make a query where you identify a visit image by exactly the four corners of its RA-det coordinates. But nevertheless, that type of information about the spatial footprint can be used in a query to help you and the butler hone in on what visit images you may want based on some sky region of interest to you. So let's print what are the dimensions that are available within the DP1 butler repo. And this has some other stuff in it, but it also generally has the things we've talked about, like tracked, patch, visit, band, among the other things, which we don't need to go into right now in the interest of time. Then the elements, again, it's kind of like a slightly broader version of the dimensions. So again, one thing that you see here that we would particularly draw attention to here is this visit detector region element, which isn't really properly a dimension, but nevertheless can be useful for like spatial queries on visit images. So now let's show that the dimensions for deep coad dataset are band, sky map, tracked, and patch, and that the return format for images is an exposure F. So you remember that the dataset type includes a storage class. So indeed, this is as we expect, but this is the exact butler syntax. So really, this butler.get dataset type is telling you kind of like the meta information about how a deep coad is defined. It's not giving you a specific deep coad. And then you can also loop over this data coordinate keys attribute in order to print out the band, sky map, track, patch portion of what we just saw in the definition of the dataset type. All right, I'll go on a couple more minutes before I pause for questions, I suppose. So in this case, we're just going to do the same thing, but for visit image, and we'll see what are the data coordinate keys, what are the dimensions. So there's this list here we were using before. We were using the visit and the detector, but you can see there's also other information, which is kind of redundant, right? So as we said before, when you know the visit and detector, you already know the band implicitly. So this brings us to the topic of required dimensions, and the way you can do that is now by looping over the .dimensions.required attribute, and this should show us a shorter list of detector and visit. And in some cases, we haven't actually explicitly specified the instrument because there's only one instrument within DP1, i.e. LSSD ComCam. Okay, the last thing I think I'll do before pausing for any questions is that, as I mentioned before, a dimension record, say for a band, isn't just our band. There can also be other metadata associated with that dimension record. And that's what the dimension schema are useful for. So if we get the dimensions as we did before from these data coordinate keys of the deep coad, but then for each of those, we print out the .schema attribute, then we can see for each dimension, what are the actual pieces of metadata associated with each dimension record And as an example, you have, say, the sky map, but the sky map isn't just the name of the sky map, right? Each dimension record actually carries some additional metadata with it. For example, patch NX max, patch NY max, which is telling you how many patches you have in each direction along the grid of patches within a given tract. And for DP1, these should both be 10 because you have a 10 by 10 grid of patches within each tract. So we only have a couple minutes left. I think I'll stop there in case there are any questions. Absolutely feel free to continue working through the rest of this notebook and the third 1043 notebook at your leisure, I suppose. But thank you for attending and happy to field any questions at this time. The sun kind of set here, so I was sitting in a light room when I started. Now I'm in a totally dark room, so whoopsies, but
You do look a little spooky.
yeah,
It's
sorry
looking
about
like the
that.
palm tree in the
Yeah, the
background.
palm
Yeah.
tree art in the background too.
That regards your face.
Well, it didn't seem like anyone experienced the Firefly issue, but we did have Frosty come online in Slack and fix it. Just some things had to be restarted. So
Okay,
if
so
yeah,
something was actually done in this in the background.
yeah, yeah. We didn't have anyone here report that they had the same issue of the Firefly tab not opening, but if you had the issue and you just didn't report it, just restart your server, just log out of the notebook aspect and go back in and it should refresh to be fixed. I'm just gonna pop into the breakout room to answer a question. I'm gonna